Okay. Let's start the second lecture in Introduction to Information Science and Engineering. The topic is New Principles of Emerging Power-Efficient Computing Platforms. As the same way as previous lecture, follow this page to submit report. Here you can see the goal of today. If you cannot answer these questions, you should be ashamed as a master of information science. At the beginning, let's assume you have three different kinds of computers. We can measure the power consumption of the computers and execution time of some specific program. In case of the first computer, the power consumption is 100 watts, and the execution time of one job is 2 hours. You can run 12 jobs per day. Now, you can see three metrics. PDP is power delay product and the same meaning as electric cost. EDP is energy delay product and the same meaning as power multiplied by delay square. EDDP is power multiplied by delay cube. Which one is best computer for you? The metric should represent smallest number on the best computer. If the electric cost is most important, you should refer PDP and take the first computer. If the profit is most important, you will refer EDDP and take the third one. The power consumption of the third computer is 3 times larger than the first one, but only 2 times faster than the first one. You will speed up the global warming. We can find a good example why we need efficient computers. In the field of bitcoins, we need enormous computing power for updating blockchain. As you know, only the first people who succeeded in mining wins coins. In this case, miners try to get fastest computers. However, we have no gain if the cost for electric power becomes higher than the value of coin. Only the person who can get efficient computers such as special ASIC takes the profit. Also, you should aware that it becomes impossible to continue spreading complicated AI system without considering the power consumption. The power budget will be severely restricted to keep zero emission, for example. But you have to understand the fundamental correlation between easiness to use and power consumption. If we have no restriction on power consumption, we always employ the power-consuming but easy-to-use computers. But what happens if power consumption becomes dominant? We give up to keep traditional von Neumann computers, or should pay huge amount of carbon tax. You have to consider which way is better for us. The reason why you should consider non-von Neumann computers is mainly for reduce the power dissipation of computer system. In this figure, the x-axis is performance per area, and the y-axis is performance per power. The lower left corner means worst efficiency in computing. I guess you already know how to program traditional von Neumann computers such as desktop PCs, smartphones, and Raspberry Pi, for example. But you can observe CPUs are the worst platform from the view of efficiency. By limiting the range of usage, we can employ many techniques to improve the efficiency of computers. For example, special purpose CPUs include GPUs, and CGRAs include Google TPU and DSAs. The upper right corner is special purpose hardware such as video encoders/decoders and mining hardware. Those are not programmable. Non-programmable hardware is not a computer anymore. Let's see the skills for getting efficient computers. The leftmost one is CPU, and typical CPU in desktop computers consumes 150 watts. For using CPU, you just need to learn how to write C or Python programs, but only 3% of 150 watt is used for calculation. The rest of the power is discarded as heat. After you get the skill for writing parallel programming such as CUDA, you can run your algorithms on more efficient computers such as GPU. The next one is field programmable gate array. You need to learn how to map your C programs on the two-dimensional structure of hardware by using high-level synthesis. The efficiency will be improved to 60%. The rest of the candidates such as accelerator and ASIC require deep knowledge on architecture, processor, memory, circuit, and device. You can improve the efficiency more than 80%. ASIC is ultimate implementation of algorithms. But we should recover initial investment. While the algorithm is being changed, we never go to ASIC. In general, we should keep programmability to increase the chance to recover initial investment. In recent years, many engineers and researchers are focusing on CG-arrays that can accelerate the processing speed of AI and other applications. The computation speed of CG-arrays is much higher than CPU and GPUs. Google already started to use TPU as their own business. They already succeeded in enhancing the performance, reducing power consumption, and improving their profit. So, the keywords for making power-efficient computers are architecture and approximate computing. How to directly connect your algorithm and device becomes more important than before. Let's see an example how to detect a slit angle in a 5x5 image. This is one of basic front-end for image recognition. The upper image is a target slit. For the detection of this kind of pattern, weight data with 1 and -1 is used. The result of pixel-wise multiply and add is 5. The result with the lower image is -1. We can find 135 degrees slit in a big image just by multiply and add with this specific weight on every portion. In this case, we have 6 different ways. Special purpose circuit, MEM capacitor, stochastic logic, ternary cam, CPU/GPU floating point matrix multiplication, and CGRA convolution. You may know quantum gate, quantum annealing, optical computer, and so on, but these techniques are just in the field of science, and not available for this application. Also, not the candidates for energy-efficient computing. In fact, a report was published from NITO and JST in 2018. A group of new principal computers only covers CGRA, systolic array, neuromorphic including MEM capacitor, stochastic computing, and digital annealing. Digital annealing is applicable only for combinatorial optimization. So, in this lecture, digital annealing is out of scope. Okay. Let's follow each of 6 ways. The first one is special hardware similar to real visual cortex. In well-known neural networks for image recognition, several layers in the front end are used for feature extraction such as edge detection and slit detection. In case of CPU and GPUs, this function is implemented as convolution including huge number of multiplication and addition. We can replace them with some small hardware and reduce the power consumption and execution time. In the neuromorphic system, by employing this kind of feature extraction hardware as the front end, new materials can focus only on the back-end network. The second one is more suitable for material science. Many papers related to neuromorphic device have been published. A variable capacitor is attached to each cross-point of two-dimensional network like this way. Input image data come from upper side, and huge number of approximate multiply and addition are performed. Each horizontal wire is the output of the calculation. By changing each capacitance, some kind of image recognition is performed. This architecture is very hot in recent years. But I don't hear some paper was submitted from the laboratories in material science. This waveform is a result of analog simulation. Tolerant pattern matching is really performed by capacitors. The third one is some kind of digital circuit, but is based on totally different idea for computation. By employing random number generators instead of traditional huge multiplier, we can significantly reduce the size of hardware. But the accuracy is sacrificed like this way. The left side is a result of traditional digital matrix multiplication, and the right side is a result by stochastic logic. This is the idea to replace a huge multiplier with an AND gate. From the left side, 2 random sequences are provided. Each sequence should have no correlation by using dedicated random number generator for each sequence. The value is represented as the ratio of 1. In this case, both of inputs represent 0.5. After the AND gate, the output sequence has 2 ones and 8 zeros that represents 0.2. The value is a little bit different from correct value 0.25, but for some AI applications, the error may be acceptable. In the same way, adder can be implemented by a random selector. The output is just an average of the inputs. After double the number of ones, we can get the correct result. If you need accurate addition, population counter and normal adder should be used instead. The detailed implementation of stochastic multiply and add for 8 elements is like this way. It seems complicated, but quite smaller than traditional 8 multiplier and adder. The fourth one employs content addressable memory. Ternary means each one bit can represent 0, 1, or don't care. Let's assume the left side images are input data, and the chem has a set of patterns in each line like this way. The first line of the chem has a pattern with 10x000 something. For the upper image, all of the input data match with the first line, and the output connected to the first line becomes high. If some other line matches, the corresponding output also becomes high. For the lower image, all of the input data match with the second line. We can build a tolerant pattern patching by the ternary chem. Chem has similar structure to RAM. You can customize the width and height of the chem according to your application. But the power consumption is quite higher than RAM. For comparing the data with many patterns, huge number of wires are charged and discharged frequently. Okay. You learned 4 approximate computing methods. From the fifth one, you can see more accurate computing method including traditional floating point operations. When we need to multiply pi by 1.5, some specific format for floating point number is required. The upper left is for fixed point number and upper right is for floating point number. The difference is in the meaning of a. In the case of floating point format, b multiplied by 2 to power a is the real value. Popular bit length of floating point format is 32 for single precision and 64 for double precision. Let's see the detail of each precision floating point format. We can express signed 0, subnormal number, normal number, signed infinite, and not a number. How about the accuracy? Let's represent pi by each format. In the case of single precision, only 6 digits below the decimal point are correct. Even with the double precision, only 15 digits below the decimal point are correct. This means even if you put more numbers as pi, the compiler ignores the rest of digits. The difference from the true value is called rounding error. Anyway, floating point calculation unit is much larger than fixed point calculation unit. For one double precision floating point adder, 25,000 of transistors are required. Furthermore, floating point calculation unit is usually pipelined to get high frequency. Many registers are also included in the unit. If you don't need floating point operations, you can significantly reduce the size of CPU and power consumption. You can see the hardware design of a floating point unit written in Verilog code. In the case of fixed point adder, just put A and B in one line is sufficient. But in the case of floating point adder, much complicated description is required for each pipeline stage. When we write programs and let computers calculate fixed point numbers and floating point numbers, we always should pay attention to representable range and accuracy. The first issue is C has no framework to detect integer overflow. For example, with 32-bit integer number, we cannot get the population of the world just by accumulating the population of each country. Int 32_max is only around 2 billion, and we have no chance to find out the overflow during the accumulation. The second issue is floating point number is not good for counting up. The representable range is wider than integer, but floating point number has only 23 bits significand. Incorrect accumulation will be observed in the case the order of magnitude is quite different like this way. The third issue is cancellation of significant digits. We learned a formula to solve quadratic equation. However, in the case b is quite larger than 4ac, b square minus 4ac becomes inaccurate due to large difference in the order of magnitude. Finally, the important bits are disappeared. You cannot use the first formula. The correct calculation is as follows. OK. Let's check whether we can convert int 32_max to accurate floating point number or not. Let's check some neighboring values. The answer is 0x4f0000000. This value is larger than original value by 1. You learned many pitfalls related to floating point operations. But you can represent data with more accurate manner than previous 4 methods. Also in the recent years, just using some tensor library or BLAS library is enough to write basic AI programs. This is the inside of a convolution function in tensor library. If we need to detect many variations of slits in 1000 by 1000 image, we need huge amount of multiplication and addition. You need to speed up the computation by employing power-consuming GPUs. The last one is coarse-grained reconfigurable array. CGRA has long history, once almost disappeared, but now proliferated. CGRA is now most promising technique that can achieve both of power-efficient and accurate computation. Traditional programs for CPU are similar to clouded and complicated roads with many traffic signals, and CPU and GPU are similar to old cars that repeat start and stop frequently. But if you can write smart programs with no traffic signals similar to highway, CGRA can run as a high-speed vehicle with no brake system. The data is always going through the data path with no traffic signals, and many calculations are continuously applied to the data stream. As you already learned, CPU executes many machine instructions step by step. CPU requires many clock cycles due to the narrow data width in each execution. Vector computers including GPU also executes instructions, but have wide data width. One instruction can manage many data, so the power efficiency is higher than CPU in some specific applications. In contrast to these von Neumann computers, CGRA is one of non-von Neumann computers. Many calculation units including floating point units are physically arranged in two-dimensional array, and specific operations are mapped statically on each unit. After the data path among the units become ready, the input data start to go through the CGRA. All of the units perform dedicated operations in a deep pipeline. Finally, the results are generated from the bottom of the network every cycle. In other words, CGRA has no instruction cache, no instruction decoder, and no branch instruction. Only flexible data path is prepared and programmed. This is the main reason why CGRA is power efficient. This is an example of real CGRA in my lab. 10,240 operations can be mapped on CGRA statically. Now IMAX2 is implemented on FPGAs. The execution time of matrix multiplication, convolution, and heavy image processing is much smaller than embedded GPU and a little bit larger than desktop GPU. The chip size will be much smaller than others if I can fabricate with 28 nm. The speed will be 6 times faster than FPGAs. Also, the performance per memory bandwidth of IMAX2 is much better than others. Here you can see the summary of today. Let's summarize pros and cons of each of 6 implementations. Now, you can fill in today's report. If you cannot answer these questions, you should be ashamed as a master of information science. After you finish the report, take photo and send by email. That's all for today.